Comparison of core type transformer and shell type transformer. In case of core type transformer, windings are placed on both the limbs. So 50% of LV winding and 50% of HV winding are placed on both the limbs. That means the windings are placed in circular form or concentrated form. This is the core type transformer. Equivalent circuit is MMF, reluctance, and magnetic flux. This can be represented as a series circuit. As the windings are placed on both the limbs, that means HV winding and LV winding are placed on both the limbs. So the flux directions in the windings is opposite, but the flux in the core is remains same. This is a square core, so that all the limbs are having same area size. These are the 4 limbs: 1, 2, 3, 4. All the sizes are same. As the windings are interleaved, so the leakage fluxes are very less. This type of transformer having low mechanical strength. This type of transformer, requirement of insulation is less, but requirement of copper is high. Windings are interleaved. That means 50% of winding is placed on both the limbs. This core type of transformers are having low MVA rating, low current, high voltage, and lower efficiency. Size of the transformer is high, but advantage is maintenance is easy, as the windings are placed on outside and the core is inner side. Cooling of winding is easy compared to cooling of core. In case of shell type transformer, windings are placed on central limb. This is the arrangement of shell type transformer. HV winding is sandwiched between LV windings. Starting from edge, first LV insulation is placed, next LV winding, after that HV insulation, after that HV winding. The cycle repeats. HV winding is sandwiched between LV windings. This is the thickness of LV winding. This is regular thickness. That means the LV winding which is between two HV windings, but at the corners which is near to core, the thickness of LV winding can be half the thickness of this regular LV winding's thickness. This is very near to core. This is the equivalent circuit, can be represented as a parallel circuit. This is main field MMF, main field flux. The flux in the outer limbs is half the flux in the central limb. Reluctance 1, reluctance 2. This is the area of central limb. Area of the outer limbs is half the area of the central limb. As the windings are placed on the central limb only, so the flux directions are in the same directions. But this type of transformer possesses good mechanical strength. Insulation requirement is high, copper requirement is low. As the sandwich windings are placed, shell type core is used for high MVA rating, higher currents, lower voltages, higher efficiency. Size of the transformer is also low. Maintenance is hard. Cooling of core is easy, but cooling of winding is tough. So these are the important points with reference to shell type transformer and core type transformer. For any type of transformer, insulation is very important. Between windings, insulation must be provided. Between windings and core, between core to body, similarly windings to body, proper insulation and proper clearances shall be maintained in order to avoid fault conditions. Power transformer and distribution transformer. Power transformer, this is mainly used for transmission networks. Rating is more than 1 MVA, this transformer operates nearly full load. Copper losses are considered for 24 hours. Power losses also considered for 24 hours. As this transformer is continuously serving the load. Iron losses equal to copper losses. Efficiency of this power transformer is very high, nearly 99%. This type of transformer operates on power basis. So these transformers are continuously transfers power from one circuit to other circuit. That means from primary to secondary. These transformers are continuously transferring power. Distribution transformers. These type of transformers are mainly provided in distribution network for load distribution. Rating can be lesser than 1 MVA. These transformers operates nearly 3/4 of the load. This depends upon load cycle. Copper losses depends upon load cycle. Iron losses are considered for 24 hours. Iron losses equals to half the copper losses. Efficiencies can be nearly 98%, but the transformer operates nearly 3/4 of the full load. Here the basis is these machines operates on energy basis. That means this depends upon load cycle. Load cycle is considered hourly load cycle per day. Morning 6 AM to again next day morning 6 AM, 24 hours. During daytime or early morning hours, the load is high. During lunch hours, the load is less. Again during evening time, the load is high. During night time, load is low. This is the load cycle. Depending upon load cycle, this transformer operates so that copper losses are depends upon load cycle and energy basis. Transformers are static machines, so there are no rotating parts. Friction and windage losses are negligible. For that reason only, these machines are having highest efficiency. Efficiency can be varied from 96 to 99%. So these are the high efficiency machines. Transformer versus rotating machines. In case of rotating machines, the EMF is generated based upon the relative space variation. Relative space variation means fluxes are stable, whereas windings are rotating. Whereas in case of transformer, this is relative time variation. The windings are stable, the flux is rotating. So these are the two conditions for EMF generation. In rotating machines, that is relative space variation. In case of transformers, this is relative time variation. The transformer rating, why we are considering in only KVA or MVA, why not in kilowatt rating? As the load increases, we go for higher MVA rating. As the load decreases, we can go for smaller KVA ratings. Coming to losses first. Copper losses. In case of transformer, the copper losses depends upon current, and iron losses depends upon voltage and frequency. So these losses does not depends upon load power factor. So transformer losses are independent of load power factor. Rating of any electrical machine is calculated with the help of this formula P equals to VI cos phi. So in case of transformer, it does not depends upon load power factor cos phi. So if you omit the term cos phi, the remaining term is only VI. VI equals to apparent power. So S equals to VI. If we take these values only, then it is VA. So as the transformer is independent of load power factor, so the rating of transformer can be taken as apparent power S equals to V into I. So the transformer rating is in MVA or KVA or simply VA. So the transformer rating is in VA.